As a final example of describing a situation with the differential equation, let's come up with a mathematical model for how a cable suspended from both ends would hang under the influence of gravity. So we're going to take a cable with linear weight density W, and linear weight density is just the weight of the cable per unit length. So this would be measured in something like pounds per foot or newtons per meter, I guess. Just tells you how much a unit length of the cable material weighs. So we're going to take a length of this material and then suspend it from 2 points. And under the influence of gravity, it's going to sort of hang down in some way. And what I'm suggesting we do is figure out some sort of description, and of course it's going to turn out to be a differential equation, of how this cable would hang. Now we might as well, just to make it easy on ourselves, put our coordinate system so that the very bottom of the cable is at the origin. We get to choose the coordinate system, so we might as well do it that way. I'm going to zoom in on this situation like this. And what we're going to do is focus on just one area along this cable. So let's start at position X and go over to position X plus delta X. So we're going to describe what's happening just along this short red segment of the cable. We'll sort of zoom back out to the full situation in a little bit. Now if we zoom in on just that little piece of the cable, we have this red piece of cable here, and let's call the length of this bit of cable delta S. Right? S is a common symbol for arc length, so delta S just means this is some small bit of arc length. And what we're going to do is, right, this cable is being held up, so what we're going to do is write the forces on both ends of this bit of cable and write down the equations that indicate that this bit of cable isn't moving, because once this cable has stopped wiggling around and comes to rest, it won't be moving. So let's see. Let's figure out what forces are acting on each end of this cable. So at the left end of the cable, right, this bit of cable is actually attached to its neighbor on the left, and its neighbor on the left is pulling that way with some tension. So let's call that T1. And of course the direction of T1 sort of depends on the slope of the cable here. So let's call this angle theta 1. Okay, another force that's being exerted on this bit of cable is the neighboring cable to the right, which is some other tension, T2, and that has some direction that we could call theta 2. And then of course the final bit of the final force being exerted on this bit of cable is the weight, and the weight of this cable is the linear weight density times the amount of cable, and the amount of cable is delta S. So those are all the forces on this cable. Now, because this cable, once it comes to rest, it's not moving, we can write equations that say that these forces are balanced in the vertical direction and they're balanced in the horizontal direction. So let's write those two equations. So first let's write the vertical forces. So let's see, what forces are pulling down? Well, part of this first tension is pulling down, and we need to do a little trigonometry to figure out what part that is. I guess maybe it's easier to draw it like this. Okay, so the part of this tension that's pulling down, since this is sort of opposite the angle here, we're going to need a sine. So the part of that tension pulling down is T1 times sine of theta 1. And then also the weight is pulling down, so plus W times delta S. That has to be equal to the force pulling up, so that, right, if these forces weren't balanced, the cable would move around, but it's not moving. So the forces pulling down have to be equal to the forces pulling up, and the only force pulling up is this tension at the right-hand end of the cable. And the portion of it that's pulling up is, again, it looks like the opposite side of this little right triangle, and so we'll use sine again. So T2 times sine of theta 2. All right, now let's do the same thing for horizontal forces. Now there's no portion of the weight acting horizontally, so it will just be the tensions acting horizontally. T1 is pulling to the left, and the horizontal part of T1 is adjacent to this angle, and so we'll use cosine. So T1 cosine theta 1. That has to be equal to the whatever's pulling to the right. And it's only T2 that's pulling to the right. And the part of T2 that's pulling to the right is, again, the adjacent side here on this little right triangle. And so we get T2 cosine theta 2. All right. Now, with this kind of situation, it's not at all clear how or even if derivatives are going to show up. I guess what we should do is come up with a symbol that represents the shape that this cable is taking. And the shape of this cable, well, it's really just a graph. And so we could call the shape that this cable takes y of x. So, but, you know, how is the derivative of this function related to anything in this situation? Well, if you look at the diagram, right, these tensions, these angles here, depend on the slope of this graph, right? And how are angles related to slopes? Well, the tangent of an angle is a slope. So I guess really what we hope to have show up is the tangent of these angles, because tangents should be slopes and slopes should be derivatives of this function, and then we'd have a differential equation. So we want tangents to show up. And look here, this top equation has some sines in it, and this bottom equation has some cosines. So we should divide sines by cosines. So what we can do is take our vertical equation, divide the left-hand side of the vertical equation by the left-hand side of the horizontal equation, and same for right-hand sides, right? Because we have these two equations, they're both, right, both equations say that things are equal, and if you divide equal things by equal things, you get equal things. So that is just another way of saying you can divide equations. So when we divide these equations, we get T1 sine theta 1 plus W times delta S all over T1 cosine theta 1. And then on the right-hand side, the T2 actually cancels immediately, and we get sine theta 2 over cosine theta 2. That's tangent theta 2. Okay. All right. Now let's continue simplifying this a little bit. We could have T1 theta 1 over the denominator plus W delta S over the denominator. So, right, we get T1 sine theta 1 over T1 cosine theta 1 plus W delta S over T1 cosine theta 1 for the left-hand side. Right-hand side is still tangent theta 2. But in this first term on the left, the T1s simplify away, and again we get a tangent. So tangent theta 1 plus W delta S over T1 cosine theta 1 equals tangent theta 2. Okay, but hold on, right, we had these tangents because tangent of an angle gives you a slope. And if we look back up at our diagram, right, so tangent of theta 1 is the slope of this line here, but that's the tangent slope at this x position. So this tangent theta 1, this is the derivative of y with respect to x evaluated at x. By the same token, over on the right, tangent at theta 2, right, that's the slope of the graph at this right-hand point, but that's at x plus delta x. So that's the derivative of y with respect to x because it's a slope, but it is the slope at x plus delta x. Okay, and let's not forget our w delta s over t1 cosine theta 1. Okay, now whenever I see a term that has x and x plus delta x, I think, oh, these ought to be subtracted, because if these are subtracted, maybe we can make a difference quotient show up. So let's move this derivative to the right. We get w delta s over t1 cosine theta 1 equals dy dx at x plus delta x minus dy dx at x. Okay, and now, you know, this right-hand side really looks like it's trying to be a difference quotient because we have a function, dy dx, evaluated at two x values that are very close to each other. These two x values are separated just by an amount delta x. So to make this a genuine difference quotient, what we should do is divide both sides by delta x, because then we'll have a change in dy dx divided by a change in x, right? And that's a derivative. So divide both sides by delta x. That's going to put a delta x in the denominator on the right-hand side. The left-hand side. So now the left-hand side is w over t1 cosine theta 1 times delta s over delta x equals dy dx at x plus delta x minus dy dx at x, all divided by delta x. Okay, now actually by dividing both sides by delta x, we actually have two derivatives that are trying to show up because we have two difference quotients. The one on the right we've already talked about, but the one on the left is a small bit of arc length divided by a small change in x. So now if we take the limit on both sides as delta x goes to 0, these difference quotients turn into derivatives. And we get w over t1 cosine theta 1 times ds dx equals, so here we have a derivative of dy dx, but that's the second derivative. So d squared y dx squared. Okay. Now remember how we set up our coordinate system, right? We have this cable hanging like this. We set up the coordinate system so that the origin was at this lowest point. So at this, right, this differential equation is true for every x value, and in particular it's true at this central x value, and at this central x value theta 1 is 0. So we can plug theta 1 equals 0 into this, but theta 1 only shows up right here in this cosine term, and cosine of 0 is 0. That makes this whole thing w over t1 times ds dx equals d squared y dx squared. Okay, now this is a differential equation, but this differential equation has two unknown functions, y and s. And that's a problem, right? We'd like to have only one unknown equation, only one unknown function, since we have only one equation. And y and s actually aren't independent. They're related because the shape of this graph, which is y, also determines how long it is, but that's s. So we should be able to write s in terms of y. Now, remember, if you have a tiny bit of displacement, a tiny arc length, if you zoom way in, it's as if this bit of arc length is straight, and right there's essentially straight bit of arc length comes from a horizontal displacement delta x and a vertical displacement delta y, and that means that, just using the Pythagorean theorem, delta s squared is delta x squared plus delta y squared. Now taking square roots, we get delta s is the square root of delta x squared plus delta y squared. Okay, now we can divide both sides of this by delta x, like this. On the left-hand side, this is delta s over delta x equals, now we can move this this delta x inside of the square root. We get the square root of delta x squared plus delta y squared over delta x squared. I should probably have a parentheses here. And then simplifying the stuff in the square root, we get delta s over delta x is the square root of, now delta x squared over delta x squared, that's 1, plus delta y squared over delta x squared, that's delta y over delta x squared. And then finally, when we take the limit as delta x goes to 0, all of these deltas essentially turn into d's. We get derivatives instead. So ds dx is equal to the square root of 1 plus dy dx squared. So that's the relationship between ds dx and dy dx. And we can put that into our differential equation up there. So we get w over t1 times the square root of 1 plus dy dx squared equals second derivative of y with respect to x. Okay, so finally we have a differential equation that describes the shape that this hanging cable would take. Of course, solving this differential equation is a whole other thing, and I think historically the people that first figured out this differential equation, once they had it written down, they realized, oh, I know a function that satisfies that equation. So they didn't actually solve it using some process, they just guessed a solution once they had the right equation.